Yes. No, yes. You know what a bow tie is, right? Yes. Have you never seen him wear a bowler? Oh, yeah. I don't think it's like. Even when he switches to like a brown shirt. Yeah. He's like that. He's from Texas. I guess. Young is ethnicity. He's German, Texan background. Who's first name? Yeah, when we needed to work in,
Okay, I got your tongue. It's a new way to get your attention. I'm going to start writing on the board. Monday. I'm surprised so many are here. I thought about not showing up. Just watching the video. Oh wait. Actually, I actually do save these videos. If I ever screw up, and by the way, if you guys could keep an eye out for the camera, I've been having some problems with it lately. If it beeps or clicks off, let me know. I might be able to fix it. I actually had my video from a couple of years ago, and I thought about just putting it up on the web and just came to the class. But I would be fired for that, so I won't do it. Other class business, let's see, I haven't posted the second hour video from last time, which is designed to help you on your homework. I'll do that as soon as I get back, just that the camera's been working lately. I should have that posted. I posted the first hour. And you got a homework due on Wednesday, and our test is actually coming up sooner than later. Two Fridays from now, is that right?
Mm-hmm.
Yeah, the 13th, right? That's 2 Fridays from now. Yeah, not this Friday. It's not this Friday. It's next Friday. Okay, so gotta start thinking about that. And then you have spring break, and then I'll have it back for you on that. Come on, guys. What's going on? It's not going nuts. Sorry, I know it's Monday. So I'll have it. All right. So you take your test Friday next, and then you have spring break, which means you're just going to work that more. Am I right? Yeah, I know, a lot of you. I mean, you know, when I was in college, the rich kids went to Florida. I was in North Carolina, so it wasn't that far, but I'm guessing most of you are just going to fit in more hours at your work, which sucks, but hey, you got to eat somehow, right? And I recommend stealing. But anyway, so we'll take that time, of course, to grade your tests. I'll have them for you Wednesday next, because I have all, there's no way I won't have it to you by Wednesday, or maybe, no, what am I saying? No, I'll have them ready by Monday. All right, now that gives you, now remember what the third Friday is? Or sorry, fourth Friday? No, that's the last drop date. All right, so if the second test has not gone well and you haven't turned in homeworks, you're going to fail. All right, and then you know it. So drop the class if it comes down to that. So anyway, I don't want that to happen, but if somebody's not had a good test and not a good first one and hasn't been turning in homeworks, I guarantee you, I'm not going to fail you, you're going to fail you. So, but you'll know that. All right, so I'll make all your grades available to you then. Any questions from you folks? Not a lot to talk about, right? We're okay? We're okay? All right, so let's just go over some more material. This is a really boring day, by the way. The material is high school chemistry. And, I mean, it's good to go over stuff in case you're like, oh, I don't quite remember. And I have a demo. I know I'm not known for demos, but I actually have a demonstration today. It's really boring. You're going to hate it. So for some of you who like to sleep in class, just go ahead and do it. I don't. I'm a little run down too. I don't know. I'm just kind of tired, so I may not be too jumpy and happy and silly today like normal. Okay, let's review old material and then get into some of the new material which you had in high school. Chemical potential. Again, is how energy changes with mass, and that can be an ice cube melting, so that would be a loss of ice and a gain of water. Remember, I'm going to call water liquid water. Liquid water I'm going to call water. Solid water I'm going to call ice, so I know they're both the same thing. And that is a very primitive chemical reaction, but it does work, and it is general. So it works for ice melting, it works for gasoline burning. And that really is absolutely true. And we learned at equilibrium, chemical potential of ice is equal to the chemical potential of water. Okay, so if chemical potential of ice was greater than that of chemical potential of water, therefore 1 is turning into 2. Okay, or gas is turning into CO2 with water because it's burning it there. It doesn't matter what it is. So an important little aspect about this, it's not going to come up again. This tells you, the crazy thing about thermo, it tells you that, yeah, it's going to do it, but it never tells you how long it's going to take. Those are the reaction barriers. So if 2 is more stable than 1 because it has less energy, which is good, 1 is going to turn into 2, but I don't know whether it's going to be in seconds or eons. There's no telling. This information does not tell you that. 346. 346, you take kinetics, and then you will get that bit, which is obviously kind of important, but we don't do it in this class. It's a little stupid. All right, so that was really all I got to. And yeah, that's really all I got to. And let me point out one other thing as well. The neat thing about these, they are all equal. And I can do I'll do 1 or 2 examples of derivations where I'll work it this way and I'll work the derivation that way. And the reason they're equal is because of what you hold constant. And remember, I'm holding constant the natural variables of whatever energy function I'm talking about. And as usual, from now on, this guy will always be the most important. In every example I'm going to do, almost every example, I'm going to do a constant temperature and pressure. And again, remember, I may change pressure, I may change temperature, and then keep it constant and then run the reaction. Hypothetically, this way. So let me point out to you, okay, let's look at this guy. So U is U, A, H, or G are extensive, intensive. Which one? Of course, they're extensive. Okay, number of moles?
Intensive.
Extensive, right. Now, remember, you can think of number of moles, literally almost the definition of what is extensive. Moles and volume are really incredibly good examples because I know it matters if I have more of them. But pressure of a big balloon is the same as the pressure of a small balloon. So that doesn't matter. So anyway, so these are, number of moles is a very good example of what it means to be extensive. Okay, now I've got extensive over extensive, which is, right. Now here's the damnedest thing. So these intensive numbers tell you whether something's at equilibrium. Okay, ice cube floating in water. What's their temperature? Remember the previous example? I forgot already. What did you do this weekend? Anyway, it's what's the temperature? 0 of the ice, right? In the water, equal temperatures. So in equilibrium, what do things have equal chemical potentials? They have equal temperatures. They have equal pressures. Okay, now think about this. I got a cup of water and ice is floating in it, and the cup is just a regular cup, so the top's off. Are they at the same pressure? Yeah, of course they are. Pressure, extensive, intensive. I just said it right, intensive. Okay, look at this. T1, you just told me that this was true, and you just told me that the pressures were also equal. Intensive, intensive, intensive. Define equilibrium. So that's kind of an important concept, and it's just, I don't know why, but it's just how this universe was created, Stephen Hawking, kind of stuff, that it seems that equilibrium is defined solely by, not only by intensive variables, by equal intensive variables, not extensive, right? The volume of the ice does not have to equal the volume of the liquid water, to be at equilibrium. That doesn't really make a lot of sense, and it's not right. So that'll come up again, actually, towards the end of the day. And, all right, so all this chemical potential stuff is going to come up in about another 2 weeks. So again, this is my usual, I am following the book, by the way, it's not my fault. I'm introducing some concepts, I'm going to drop them, and then they'll come back later. So I know that may be a little annoying, but again, I kind of have to follow the book to some degree. And by the way, the calendar is on time. We're pretty much right on top of the calendar. If you're not following it, who cares, right? Just follow the videos. A little reminder. Okay, so I'm switching gears, and I'm going to go into that stuff in high school that you had. You remember? You folks remember Hess's law? Yeah, A and B, A goes to B and B goes to C, so you figure out that A goes to C, and the enthalpy, and the delta G, and the delta S, and all that stuff. Unfortunately, we're going to do it again, and I know it's going to bore you to death, so again, if you're asleep right now, sweet dreams of dragons. And what to say about that? Let's start with enthalpy. And I want to remind you again of a little derivation that I could ask on the next test because it is very easy. It's always good to see things multiple times, right? TDS minus PdV. Remember how to do your Legendre transforms because I cannot imagine that they won't come up. So I got TDS plus VdP and constant pressure, because again, we live in a constant temperature, constant pressure world, and you know that enthalpy is heat. Okay, now just to remind you some details. Okay, so enthalpy is going to be heat because we're going to do everything at constant temperature, constant pressure from now on. But remind yourself, if something is endothermic, what sign should I have here, greater or less? And not equal, it's not going to be equal, okay? Everything's going to produce or consume a little bit of heat. So what do you think, less than or greater than? Again?
Greater than.
Greater than. All right, wait, what did I said endothermic?
Enthalpy. I mean,
Hold on one second. Greater than. Positive. Right. And so, sorry, I actually did confuse myself there for a second. So this is endothermic. Endo. Might be snooped on. Anyway, so remember what's happening is this is a chemical reaction that got cold, and it's cold because I'm touching it, and I'm feeling it's cold, and that's because my heat is going into it. And so heat into the system is positive, right? It's a good thing to store energy. Just remember that little mnemonic. And delta H is negative. Obviously, no, that's exothermic, so it's getting hot. Now, here's the damnedest thing to remember. Again, we're in a constant TP world. And so I know that this is going to tell me how the entropy of the outside changes. Remember, total entropy, not, one of you actually made a mistake on the test. You said only the entropy of the system, that has to increase. No. The entropy of the system and its surroundings has to increase. The net sum has to increase, or the reaction is not spontaneous. Now, this is going to represent the heat outside the system. Now, as you know, most reactions are exothermic. Right, this guy usually wins. Most reactions do this. Although, of course, there's still cold packs. Of course, some things are endothermic, like salt melting is endothermic. But most reactions, like burning gas, are exothermic. It's a practical thing. It doesn't have to be. It just wants to be. Because you're increasing the entropy of the outside. So that bears repeating. S. So surrounding is going up. Or better yet, I like this. I like doing it better this way. It's positive. Okay, so you're winning. Not like Charlie Sheen, and God knows what he did to win, such a white powder. But no matter what, you've increased something's entropy. And that means that this is going to help. This is going to help the total. Now, it's true that not every exothermic reaction is still going to have a negative delta G. And that's because the interior can be losing so much entropy, the gain of the outside is irrelevant. And the total is negative, and that means it's not spontaneous. That reaction will not occur. It's just that it doesn't happen that often. So again, just a little blah, blah, blah on why reactions tend to be exothermic. And also, I do a lot of synthesis in my lab for a physical chemist. Why is this dangerous? I tell you how accidents occur, because I've had some fires. So what can happen is, if a reaction is exothermic, the one reason you use a solvent, why do you have to have solvents? You can do some chemical reactions without solvents. You better know what you're doing, though, if you do that, and know that it's safe. Because most of the time you want a solvent. You want a solvent to keep the reaction cool. If reaction gets too hot, two things can happen. For one, several different reactions can start occurring. You start allowing your A to B not to make C, but D, E, and F, and G. And you probably don't want that, right? So you want to keep this solution cool, and you, again, do it with the solvent. You put the solvent in the ice bath. If you screw up, if you had not enough solvent, the exothermic reaction can start to boil the solvent. And guess what? That's probably going to speed up the reaction. Again, it's a practical thing. Making more heat, making more solvent boil. If the boil off is incredibly fast, the reaction vessel, even if open, will explode. And then you've also probably started a fire at the same time. So anyway, that's how most accidents occur. Not because of toxicity, because of heat. And, okay, so when it comes to Hess's law, Hess's law is all about the first law that says that energy cannot be created or destroyed, And it means that, God, I know I've said this a couple of times, but it's something I personally have a hard time getting my head around. And that is, again, the table in the back of the book. Here, just a little bit on the side to remind you of high school chemistry. Look at the table in the back of the book. You have delta H, the formation. You've got a delta formation G. You've got an entropy. And this will be, these are per molar quantities, so this is the correct symbology. And you generally have a heat capacity at constant pressure, which is generally, again, relevant because we do reactions at constant pressure, unless you're crazy. And then you've got, water, methane, blah, 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 and then the table is filled. Okay, again, notice the thing that's really important. There's no heat of formation, G of formation, entropy, not the entropy of formation. You can calculate how much entropy is generated by making something. Of course you can, by products minus reactants. But this is not the same as these. It's not. It doesn't really practically matter, but I want you to know why this is. Again, energy can be computed in a relative way. And so when it came to entropy, for reasons I talked about last time, I don't like relative entropies. I want absolute entropies because I need them for other things. And we're going to get into it. But these guys, no, not really. Now remember, I could have created the table like this. And don't write this down. I'll put it right back up in a second. I could have made a table just like this, except that it's it's very time consumptive and energy consumptive to measure the absolute G and H for everything. It's just going to take a damn long time and cost a lot of money. But these guys are cheap and easy. This is very easy to figure out. And again, these are formation H's, formation G's. This, whatever this is water, this is how much H and G I get from making water from oxygen and hydrogen. All right, this is methane. This is how much heat and G it takes to create methane from actually graphite and hydrogen, right? So, and I'm going to get into that. And again, it's because everything's relative. Now we've got to figure out what the relative state is. So that's our notion of standard states. Standard states. Okay, so while I'll get into more details about formation and really try to get your head wrapped around it and why we don't calculate the absolutes, first you've got to note that, of course, H and G are going to change, and S are going to change if you change temperature and if you change pressure. If you do that, then these numbers are altered. So you have to pick, you've got to pick some things to hold, to make the measurements to begin with. All right, so you're going to have to decide on a temperature and you have to decide on a pressure. Notice that those are intensive variables, right? Intensive variables that define equilibrium. Okay, so I'll tell you that there's only two standards that you want to know. For one, everything is per mole. That's brainless. I'm not even going to write it down. But I'm pretty sure that these numbers, all these numbers in here, come from a particular measurement made at a particular temperature and pressure. And then we're done. Okay, what do you think that temperature is? Take a good guess. 25 degrees Celsius, that's right. Of course it is. Because most of the world is about at 25 degrees Celsius. It makes sense, it's practical. I'm not going to do this at 0 K. The whole point was not to do this at 0 K, to make the standard temperature 0 K. It is for entropy, but not the others because it doesn't have to be. This is easy. That's why we do it this way. Okay, now this is a good one. I like this one. Because you're about to tell me the wrong pressure. What do you think the standard pressure is? 1 atmosphere. And you're wrong. 1 bar. 1 bar. This guy's funny. He has to be up here and appreciate it. Let me guess. Was the first group the chemists and the second group the engineers? Did that just happen? Some of you are shaking your heads. I don't know. Anyway, that was funny. Okay, 1 bar. Now, how does 1 bar compare to 1 ATM? Is it about the same? Is it more? Is it less? Yeah, it doesn't work. Okay. Remember that 1 bar is 1,000,000 pascals. And remember that 1 atmosphere in pascals is 101.325 pascals. So 1 bar is a little bit less. Okay, and again, now remember, we're picking standard states to fill this table out, to make measurements at standard states, and I get the table, and I'm doing this in a very practical way. So why did we not make pressure 1 atmosphere? Anyone want to venture a guess? It's kind of a cool concept, really. All right, so tell hey, you don't need to talk to this, fine. Where is atmospheric pressure 1 atmosphere? Where on land?
At sea level.
Sea level. Begins with a B. The beach. No one lives on the beach unless you're very rich and then you get wiped out by typhoons. All right, most of humanity lives slightly away from the beach, where the pressure is slightly lower. Right, we're actually here. I think I looked it up. We're 700 feet, something like that. Which, by the way, you ever want to guess what the height of Niagara Falls is? Same number, right? We are elevated because of Niagara Falls. And I saw that because I watched the Discovery Channel too much. As Niagara Falls slowly gets chopped backward because of the water, when it hits Lake Erie, all the Great Lakes are going to drain. So I just can't wait to watch it happen. It's going to happen in 10,000 years, but I'm going to live forever. So anyway, so that's how I know what pressure we're at, what elevation, and of course our pressure is slightly less than 1 atmosphere. Again, it was just a very practical thing. You try to remember this. Now this one's brainless, but this one does take a little bit extra effort to remember. And then let's talk about calculating delta H's. So again, one reason that we do things the way we do is because of the path independence, and the path independence of these energies comes from the fact that they're state variables. And so basically what this is all about is, so I've got my reference state for all these chemicals, whatever they're at, whatever they are, and of course I'm going to set off a chemical reaction, and so this is going to change. It's going to change the H content of whatever the heck is in the pot. Now here's the thing, it doesn't matter. Now again, remember this is heat. This is a change in heat. So let me do this. Let me just point out that this is the change in H. And of course, a constant pressure, temperature world is a change in heat, and that could be reversible. That could be the reversible heat, but we could also do this. Sorry, I wasn't reversible. It could be irreversible. It doesn't matter. We're still going to calculate the same change in H, no matter what the path is. Meaning that we don't have to go as crazy as we did with entropy and freeze everything in a bomb calorimeter and let it warm up to 25 degrees at 1 atmosphere pressure. That is what we did with every material that we can get our hands on to calculate this, but we're not going to do it for these because we don't have to. And we don't have to because of exactly this right here. So, okay, so Hess's law, let's do some very simple examples. Childishly simple, and then I've got a demo. I know you're not used to demos. I'm kind of bad about that, but when I was in grad school, Berkeley really did a very, very poor job with freshman chem. They only taught it 2 days a week. And I don't mean for an hour and a half. I mean Monday, Wednesday, and no Friday, which was pathetic. The students knew nothing. In fact, you folks are more likely to get into grad school than UC Berkeley students. And a lot of people that know that's not true. That place is great. Great for what? Great for research. You're not doing research, you're undergrads. You're going to go to grad school and do research. This is not helping you. So I was always kind of shocked at that. The reason I bring it up is, actually I forgot because I was talking so much. So I don't spend a lot of time on demos because they did. So not only were they not teaching very much, they also spent a lot of time on demos that really kind of ended up being a waste of time. So the question is, so let's look at water boiling. And I have to be careful with this. These are the phases. And I'm not going to write that down. This is quite easy. So I'm at my standard state. And so I'm going from liquid to gas. Look at delta H. And that'll be for a mole. And I will often not write that down. I'll try to remember. Let's see, it's 44 kilojoules per mole. Now be careful because sometimes I might forget the per mole. I just drop it. Everything's per mole. Okay, and then of course, now remember that this is all at STP. Now again, symbology. Symbology is that at STP, you pick up this little stupid symbol here. Oh, it's probably too small. Sorry, so you get this little circle with a line in it like a little theta. And that means that this is at STP. Again, there's a lot of symbologies that are going to come up, and I'm going to try to get them right, but sometimes I'm going to screw up. And so now I know. So I make this measurement, and now I know. Any of you have a question about that? Is there anything a little strange? What's strange about this? This is water boiling. What's strange about it? I'm telling you, there's something very strange about it. What is it? Huh?
Should it be negative?
No, because it takes heat goes into it.
Temperature.
Right? Temperature? What about the temperature?
Temperature, water boils at 100 Celsius.
Right, at 100 degrees, not 25. So how in God's name do I know that? How can I know this number if this process doesn't occur? That's a very strange thing, isn't it? Okay, are you ready for the demo?
Yes.
Okay, here it is. It's water. Pretty crappy water. Got it from the toilet. Well, anyway, actually I didn't do that. Okay, all right, so I got water in a cup, and it's clear so you can see what's going to happen, all right? All right, now, okay, you ready? You ready? Good, it started. Step right. Just wait. Just wait for it, wait for it. This is the most boring lecture ever, isn't it? What's going to happen?
Reaches equilibrium.
It's going to, well, it's at equilibrium. I mean, I just drank a little bit, but it's at equilibrium.
Okay.
If I come back tomorrow, what am I going to see? Or come back in a week, what do I see? Empty glass, right. It is going to evaporate. So here's an important lesson we're going to get into a little bit later when we talk about phase diagrams. Just because water boils at 100 doesn't mean that it doesn't vaporize at 25. It actually still does it. And the reasons by that are actually the kind of thing you learn in grad school. And I'll show you without doing any math, so I'll draw you a picture. Not today, another day, when we get to phase diagrams. But yeah, so here's the thing. Us people are very clever at filling up that table that table. We're very clever about filling up this table at STP for things that don't occur at STP. Because if I'm going to burn hydrogen or methane, that's going to get pretty freaking hot. Yet the numbers in the table in the back of the book are valid because of very clever tricks, the tricks that people play to get these things. So in this case, I can just simply wait it out. I can put it in the calorimeter and let the water evaporate. And calorimeters, we have really good calorimeters. They work really quite well. All right, but we all know that this really practically doesn't occur. And that demo is going to take a couple of weeks to do. So instead, let's do, okay, this is an aside. Let's figure out delta H for 100 degrees. And the way to do that is to H2O liquid. Looks awful. Sorry, OCD. Liquid, and that'll be at 25. You're not supposed to write it this way. I'm just doing this for the hell of it. H2O liquid is going to be at 100 degrees. Okay, and the way I calculate this is I have 1 mole times Cp per mole and times delta T, and I'm telling you that that is so 1 mole times 75 joules per k mole. Sorry, I'm getting right bad today. Times 75K equals 5.63 kilojoules. Oh, you know what, actually, I'm not being stupid, sorry. Let me just get rid of that so that I can do this per mole. Sorry, I'm going to screw up on my part. So there we go. All right, that's pathetically easy. Now what we're going to do is take H2O liquid, which is at 100 degrees C, and it's going to turn into H2O vapor or gas at 100 degrees degrees C. Okay, again now, in that case, you simply have to figure out, you have to just do the measurements, and I can tell you that, oh, God, sorry, the board looks awful. Incorrect notation. The vaporization enthalpy happens to be 41 kilojoules per mole. What's wrong with me? Sorry. 41.0 kilojoules per mole. So again, symbology, delta process what? And there's no little theta symbol because we're not at STP. So I'm actually technically doing this correct. Okay, so note that if this is an equation, this is A to B and B to C. So if I do this and write what's left, I've got H2O liquid at 25 degrees C going to H2O gas at 100. I'll toss this up if you're having trouble seeing. And the total process, and again, it does not give a symbol, is 46.6 kilojoules. So, notice it's ever so slightly higher than letting water evaporate at room temperature. Why do you think that is? I mean, you know water boils efficiently at 100, yet it actually takes more energy. Why would that be? It's this step. You had to heat it up, right? You see that water actually does boil more efficiently at 100 degrees C. It actually took less energy than to do it at room temperature. But you had to get it hot to begin with, so you actually ended up losing H. And this is positive, so this is you losing energy, right? You had to supply heat, you had to burn a stick, or burn nuclear fuel, or burn coal to get this to happen, which is all kinds of bad. But then again, drinking toilet water is also bad for you too if you don't boil it. Okay, now what I can do is complete the cycle. Let's see if we can get that number back. And to do that, I'm going to add in H2O gas at 100 degrees. What I can do is I can turn steam and I can cool it. Again, because we're very clever. And the way you do that, oh God, I'm sorry, I really screwed up using the board. So again, Cp delta T is equal to, I've got the numbers, 33.24 kilojoules. Is that right? Sorry. No, joules per, sorry, that's joules per K mole, times minus 75 K is equal to minus 2.54 kilojoules per mole. And so, sorry, I really screwed this up. So that means H2O at 25 degrees C liquid goes to H2O gas at 25 degrees C. I sum these up, and sure enough, I get 44 kilojoules per mole. So there you go, same as here. Okay, so now, again, the point here being that I don't know if they actually literally took 18 mils of water and measured the heat it took, that it captured from the outside ambient temperature that we have, and waited for that 18 mils to evaporate, and then the calorimeter spit this out, or did they actually just heat water up to 100 degrees and then let it turn to steam and then cool the steam back down again? Which one did they do? I'm not sure, but it doesn't matter. You get the same thing. No matter what, you get the same thing. And this is just an example of the clever ways that we have of filling out this freaking table for processes that don't occur at STP. So, and then there's other consequences as well. Other consequences include the fact that if you're thinking about this, well, what happens when I do a reaction not at STP? Well, two things. For one, all the numbers are going to change, so you have to figure that out. And you've already seen how I take care of enthalpy and temperature. you're going to use heat capacity. So when we do have a process that is getting very hot, like when we're going to do gas burning, methane, natural gas, when we do that burning, it's going to be hot. And so you're going to take that number from the table and you're going to tack on this term, and that'll be the new enthalpy. And then you got to figure out how S changes, and then you've got how G changes when you're off the temperature. Also, these numbers are for pure substances. I already warned you about this. It's actually, unfortunately, very painful when you start mixing things together to make them react. These numbers become invalid. And they come invalid by kind of a lot. So you have to correct the H's and G's and S's for materials when they mix and when they change temperature. And I'm going to throw a couple of you a couple of homework questions on a couple of homework questions, but I'm not going to add that stuff on the test. We're going to get to that next time, how you alter temperature. A couple of examples, and I'll have it on the homework because you have to use your graphing calculator to solve it. It's not something you can just write down and punch numbers in the calculator. I won't have them on the test, but I do want you to at least know how to do it because it's just kind of important that you know these things. Okay, other things to note, properties of the table in the back of the book. Also remember that, I'll do this example, for example. Okay, methane burning, again, that's natural gas. Oh, and I got it. Oxygen is always a gas. There's the CO2, the gas, which is unfortunate. It's 2H2O. Also, that would be a gas because methane burning is hot. So, there's a couple of cool things, again, just so you know exactly how we can do these things. What we have are little devices where what we can do is not just take a balloon of methane and then just hit it with a candle with a spark. That'll work, but it's a little bit out of control, and I may not have a good way of measuring the heat given off because it kind of goes boom, right? So I don't know that that's an easy measurement to make. But we have these little devices, they're like fuel cells, they pretty much are fuel cells, that allows this kind of reaction to occur without generating a chain reaction that goes boom. So I can actually put this membrane and add methane on one side, oxygen on the other, and let them diffuse and react together inside of the matrix, which doesn't let this reaction go out of control. And it can maintain the temperature because it's kind of a big device. It just has a lot of heat capacity. And then I can measure how much heat is generated because the whole thing's in a bomb calorimeter. You can actually do that with hydrogen and oxygen. That's a fuel cell. That's actually the space shuttle's batteries are fuel cells. In fact, we actually had a chemistry seminar. You folks, you can come to the chemistry seminars, you just won't say anything. That's a real big faux pas. And the guy was talking about the future energy needs of the world, which was scary. It's really bad. It's a very messed up story. And he was mentioning how he was actually trying to develop better fuel cells and how there is some people, I know you've all seen the Tesla, which is awesome, and it runs on lithium-ion batteries. And I even mentioned about lithium air batteries. I mentioned that in class. That's as powerful as a gas engine. But he thinks that we're actually going to be able to run cars off fuel cells. And the idea behind that is that we're going to have a ready supply of hydrogen. Does anyone know where do we get most of our hydrogen?
The ocean.
From what?
The ocean.
No. But, well, kind of. Offshore oil rigs. It's actually a large byproduct. When they dig in the ground and they dig the oil out, they often hit pockets of hydrogen gas. And so that's where we get a lot of it. And there's another thing that we do called steam reforming. I'll tell you more about that a little bit later. It'll be one of the examples of hydrogen. So if we do have a ready supply of hydrogen, you can make a fuel cell. And again, the same principle applies. You get oxygen on one side and hydrogen on the other. You force them into a little matrix where they react. They actually generate electricity. And we can again measure the delta H's of these things. But normally, of course, if I have a balloon of hydrogen, I set a candle to that, that's actually more explosive than this guy. So I don't want to do it that way. Anyway, I'm kind of just ranting at that point, just so you know about future energy needs and whatnot. Okay, one thing to note that for 1 mole of CH4, oh God, I'm really off today. The delta H, this happens to be minus 802 kilojoules Well, it would be 1.8 kilojoules, minus 802 kilojoules per mole, but I have 1 mole. So I've gotten rid of the per mole. Detail, that doesn't matter. Okay, note that these things scale. For 1/2 mole, delta H will be exactly 1/2 kilojoules. Wasn't the camera, was it? The cell phone's the camera still? I think it's still
It's still
working.
good.
Okay. So, again, energy is extensive. This is brainless, right? You had this in high school. For energies are extensive, so if I have half as much, I get half the heat. Also note, to calibrate your thinking, that's a gigantic negative number. I mean, that's absolutely freaking huge. Methane burns hot, but you already know that. So, now you also are going to run into weird stoichiometries when you look at the table in the back of the book. And how do you deal with that? Let me give you an example of ammonia. So like a lot of the examples I like to use for this part of the class is ammonia production, because that's fairly, ammonia and sulfuric acid, those are like our 2 most produced chemicals in the world. Sulfuric acid for mining, ammonia for fertilizer, actually. For cleaning the bathroom. Well, yes, but more important for fertilizer, because we need something to eat before we worry about keeping ourselves clean. And so you're going to run into these weird stoichiometries a lot when it comes to this Hess law stuff. And so let me just show you real quick how to deal with that. Remember, hydrogen comes as H2, and that's where we get ammonia. So this is also another example of our world energy economy and how it's kind of screwed up. We make lots and lots of ammonia, an unbelievable amount of ammonia, especially in Europe, by the Haber process. Anyway, it's a detail. You need lots of hydrogen for it. And again, the ocean, that's where we get our hydrogen. It should be the ocean. That would be a really good source because it's full of hydrogen in the form of H2O. But I have to use electrolysis to get it out. Well, guess what? All right, so I'm going to get hydrogen out of the ocean, water by electrolysis. That does work. Now, guess how much energy I get back? So there's energy in, right? I have to take 2 wires and plug them in, and then I collect all this hydrogen. And that hydrogen I can burn with water, I can burn with nitrogen to make things I need. Guess what? You have to input heat and then you output heat. Guess which one's greater? Input, right? The electrolysis of water is a very high energy thing. So the products you get out of it will not give you that energy back. Whatever you're making, when you're making your car go with a fuel cell, or you're trying to make ammonia so you can make fertilizers and cook, it's energetically not worth it. So our hydrogen again comes from the oil industry, or this other process called steam reforming, which will be an example. We'll probably have it on the homework. So anyway, this guy's always been a major problem for us. And if we could just get a hold of all that hydrogen locked in the ocean, we wouldn't have an energy crisis whatsoever. Oh, here's another little factoid, because I'm just rambling my mouth completely, and then I'll just stop. What was I going to say? Okay, so electrolysis of seawater gives us lots of hydrogen. I'm saying the energy input is really kind of bad. So why don't we connect a solar cell, right? Get our best solar cell. Our best solar cells are made of silicon, and then just wire that into the seawater and let it collect hydrogen, and just sit back and wait. Yeah, I know it's not going to be very efficient, but just sit back and wait. Why don't we do that? Why aren't we doing it? Anyone know? Guesses? This is kind of a terrible thing. And I'm full of terrible information. Want to talk about cancer? No. Well, you can say yes. So again, silicon is our best solar cell. It makes about 1 volt of electricity. Guess how much voltage you need to split water to hydrogen and oxygen? Of course, we just want the hydrogen. It's more than a volt. That's the problem. You can wire up your solar cell, put it into seawater, nothing happens. It's called an overpotential problem. It's the solar cell ought to have just about the right amount of juice to split water, but water thermodynamically requires more energy than it actually formally takes to split water. It's a practical engineering problem that water just is recalcitrant to accept the energy that it's being offered to split, which is enough, but not it's just being a little donkey, a little jackass. So what you have to do to make it work is you have to get one solar cell out of like a silicon material, and you have to stack another solar cell made of a slightly different material, and another solar cell on top of that. And you have to get about a stack of 3. And because they're different materials, they have different voltages. But like when you wire batteries together, all right, if you do that in series, what happens to the voltage, all right? 9-volt battery plus 9-volt battery in series is a what volt battery? 18, right. So you're just, if you do a parallel, that doesn't work, but if you do a serial, then it does work. So what you have to do is build at least three solar cells, one on top of the other, and then you can generate the voltage needed to split water into hydrogen. You know what's wrong with that? It's expensive. That's the damnedest problem. So we do have solar cells. We can turn that seawater into hydrogen. We can drive our cars with it. We can make ammonia with it. Except that damn solar cell costs an unbelievable amount of money to make. It's so expensive, it's not worth it. Oh, and guess what? So we have to get these solar cells, and we have to fill over all of Arizona. And we've got all our energy problems taken care of. Google search this. You can Google search this. The best solar cell ever made, this stack of 3, was made, with perfect crystallinity, so it worked really well, made by a company. And so, thinking, well, hey, there is a future then. Look online for this. It's a really interesting story. I actually put it in a test for graduate students not too long ago. The company that made it was, of course, they wanted to promote themselves and their products, so they showed the solar cell. They showed the solar cell that they had made on someone's thumb. It was about this big. Now remember, we have to get that and cover Arizona with it. By the way, people, that's what that means. Okay, real quick, and then I'm going to let you go. Okay, so you look this up and you see delta H per mole is minus 46 kilojoules per mole. Hold on. Okay, note that this is for, okay, again, the stoichiometry is weird because if you want to be nitpicky, you can't have half a molecule of N2. That doesn't exist. But of course, I'm not going to react just one molecule of nitrogen with hydrogen. I can easily have half a mole of N2. That's like 11 liters. I can certainly create a balloon of 11 liters of nitrogen and run this reaction in some kind of heated silo. But anyway, so again, this is for half a mole, 1/2 mole of N2, and remember your scaling laws. 1 mole of N2 react, you get minus 92, and if you have 1/4 mole N2, sorry, my handwriting is really awful today. That is minus 23 kilojoules per mole. Sorry, my handwriting is really bad today. All right, now when it comes to defining formation enthalpies from the table that I just erased, that's based on, so what I've done here, so this is technically the formation. So I need to add this, sorry, I'm writing over my own notes. This is technically the number you see in the back of a book for the delta H of ammonia. Those numbers come from, at standard state, making these new chemicals, again, the guys on the left-hand column, from making themselves from elements in their standard states. The standard state being that they're gases. Because I know at STP, nitrogen's a gas, hydrogen's a gas. So I make this correct mixture, I make ammonia, I make the measurement of how much heat was given off, so this gave off heat, right? And then under ammonia in that table, that's the number that I write. And the reason is that this reaction technically has a delta H of what? 0, right. So the whole idea behind this, for the numbers being formation enthalpies at STP, is that, again, everything energetically is relative to everything else. And those numbers are the how much heat was generated by forming whatever entry in the table from elements in your standard state. And I've gone too long, so we'll stop there. Come by office hours if you have more questions. And I will put all the videos up by the end of the day. I'll see you all on Wednesday.